Okay, guys, I'm going to make a start. Good morning. Hello. Thank you very much. Okay, so where are we? Right, on Friday, those of you who were here, we made a start on what is a branch of computer graphics called hidden surface removal. Essentially, what we have at the moment, after we've done our clipping, is we have a series of load of polygons which we want to see on the screen. If we were to brush render all of those polygons, it would look like a mess. Okay, so we'd still have to do something. And what we do is we remove these hidden surfaces. And we looked on Friday at a very simple method called backface culling, which essentially checked each polygon. If it's facing the viewer, which means if the normal to the polygon is pointing towards the viewer, we plot it. If it's facing away, we ignore it from this point onwards. Okay, so once we've done that, okay, I've done this to my virtual world of a village. This is what we get. Okay, you can see it doesn't look very good. It's the church, which should be in the background, is in front of the house, which should be in the foreground. Nothing should be in front of the house. That's the closest object to the viewer. So something's gone a bit wrong. But it hasn't actually gone wrong. It's just we've got to do another stage in the hidden surface removal process. And this stage is called Painter's algorithm. It's very, very easy. It's going to take me about 10 minutes to explain it. Okay, so it's quite straightforward. Okay, Painter's algorithm, it comes from the steps that an oil painter uses when they paint a scene. Now, do we have any artists here? No artists. You're all math students, so you're not, you don't like art. Okay. Anybody? So you all hate art. So I'm guessing nobody's painted with oils before. Okay. So what do you do when you paint with oils? You? Okay. Oh. Okay, fair enough. I'm not an artist. The last time I picked up a paintbrush was probably an art class back in school. But apparently, how you paint with oils is you have to paint the background first. So if you were to paint a landscape, you paint the background first, then you create the middle ground, then you create the foreground. Okay, so this, because oil paints apparently are opaque. I never painted with them. I'm not an art expert at all. What's the other type of painting? Is it watercolor? Apparently, is that sort of see-through? Is it a bit? Okay. So, okay, we've got no. I'm happy. I haven't a clue about this stuff. All I know is that oil painting, you have to start with the background. That gives its name to this algorithm, Painter's algorithm. So with Painter's algorithm, we start with the background. We start with things which are furthest away from the viewer. So this is written in quite sort of posh, again, presentation of the algorithm. Sort of this is how algorithms are meant to be introduced and presented. So essentially, after we have done the backface culling method, we're left with a set of front-facing polygons. So this isn't all of our polygons in the scene. It's only those ones which are front-facing. Okay, and what we do is we sort the polygons into descending order of the smallest z coordinate. So a polygon is going to, let's say we've got a four-sided polygon. That has four corners. So we've got four z coordinates. We just pick the closest. So the closest z coordinate for that polygon, and we sort the polygons in descending order. So starting at the highest and going down to the smallest. Once you've sorted them, for all polygons in P, now P is your going to be your sorted list. In the order they're sorted, you render the current one. So in other words, you start with the one furthest away, and then you render that one first, and you go the next furthest, and the last one you render should be the closest. The rationale being is if they're all opaque, the closest polygon is going to obscure any polygons further behind. So an absolute sort of very, very simple algorithm. Okay, and this is how it's sort of meant to work. Okay, if you've got the eye on the right-hand side, sorry, left-hand side, Okay, looking to the right. So this is your viewing position, and we have 3 polygons here. So A is furthest from the viewer, B is next furthest, C is closest. So if I was to do sort of sight lines, okay, so these dashed lines are lines going from the eye to the extremities of the polygons, you can see, but in polygon A, I'll just about make up this sort of edge of polygon A, just here. B, I'll be able to make out this portion of B, and C, because it's the closest one, I'll be able to see it all. So in other words, if I'm sort of trying to plot this in 2D, this 3D seen in 2D, this is my polygon A. Okay, and the next closest is polygon B, which kind of overlays it a bit. So you can still see a bit of polygon A, okay, but B overlays that sort of portion of A. And finally, C, closest to it, overlaps a portion of C and also some of A. So we can actually still see some A, but not a lot. Okay, so that's Painter's algorithm. Very, very simple. Does require a sorting approach. Okay, so we do have to do a sort of the Z coordinate. Okay, what I'm going to do is hopefully in Matlab's up and loaded. Yeah. So what I'm going to do is just show you how to sort in Matlab. Can you see that? Okay, I just increase the font size. Every time I do this, somebody must reset the font size back on these machines. Annoying. I'm going to track them down. Okay, right. So just whack the font size up so you can see it. Okay, so I'm going to create a random array. Call it A. Oops. Rand. Give it a bit more numbers. Okay. So there's a load of numbers, A 1 through to 6. Dot that to make it. Okay, so A 1 through to 6. If I want to sort that in Matlab, okay, the simple command is sort. Just going to move it up to the top. Sort A. There you go. So it sorted it into ascending order. Okay, so it started at the far left. We have the smallest number increment going up into ascending order. With Painter's algorithm, we need descending order. Okay, so all we do is instead of going up, you go down with the option descend afterwards. Okay, so if I do this, okay, so this essentially flips that sorted one the other way around. So we're starting with the largest number, going down to the smallest. Now, why am I showing you this? Okay. Part of your hidden surface removal assignment, well, the hardest part of it, so if you really want this sort of 100% extra marks type thing, is to apply Painter's algorithm to your village or to your virtual world, whatever it is. Now, to do that, you need to sort by that Z coordinate. Not only that, but you need an index of the sorted array. So what do I mean by that? Okay, I'm going to go back to just print out A. Let's say these are my Z coordinates. If I was just to sort the vertex coordinates, I'd balls it all up. Because if you think about it, the village or the virtual world I have, if I was just to sort all those vertex coordinates, that would mess up all of the polygon array. Because remember, our virtual world is expressed in terms of poly and vert. So I don't know whether I've got it here. Oh, yes, I have it here. Okay, so this is my virtual world. Let's run this program. Hopefully it works. Doesn't seem to be. Okay, right. So, oh, there we are. Boom, boom, boom. Okay. Hopefully I haven't got the answer on here. This might be the completed one. Just a sec. Oh, yeah, I have. Okay, but I won't show you it just yet. Okay, so our virtual world is defined by poly and verts. Verts is all the coordinates of your vertices. Poly is which vertices does each polygon use. Now, if we'll just to sort that using the sort command, we balls it all up because it would make it all done the other. Hello, you're right. Okay, so if we were just to sort the verts array, we balls it all up. So what we've got to do is a neater way of doing it. Okay, there's my array A, is to actually get the index of the sorted array. Okay, so doing it like this. Now what this does is that tilde means it's nothing. Tilde just means I don't want anything there. Comma index means, okay, what it's going to do is it's going to sort A, but leave A alone. It's going to give me the index of A. So if I do that, okay, so that's index. So what that means is the 6th number in A is the smallest, the 3rd number in A is the next smallest, the 5th number in A, and so on. Okay, so that's useful. So when we're doing our virtual world, we can sort it without messing up all the coordinates, but get the indexes. Then, if I wanted to, let's say I wanted to print off, the descending values of A, I can just go in a for loop, I equals 1 to 6. What is A index I? So that's printed off. Okay, so that's printed off the increase in values in A. The index is an array. The ith term in index gives me what is the ith term in the sorted. Okay, so that's a bit of help. That's for the hardest sort of part of the hidden surface removal. Assignment. Okay. That's all well and good. So Paint is quite simple. You just render the furthest thing away, sorting it to the closest. But it does fall down. And the reason it falls down is you can have overlapping polygons. So if you have a look at this figure, okay, 3 polygons. This sort of vertical polygon is over the top of this one, that is underneath of this one. Okay, this one's over the top of the vertical, underneath this one. And you can see there's kind of like a lattice type thing going on. Which one is in front and which one is behind? Which is the furthest back? We can't tell. Because if we were to tell, each one is in front of one and behind another. So it does fall down. So what Martin Newell did with the teapot fame is he came up with a method which is used in Painter's algorithm called Newell's algorithm. What it is a sequence of tests. And a sequence of about 5 tests. If any of the tests give a false result, you're fine. Okay, you don't have to do anything. If you get to the end and all of them have been true, we have to do something. Okay, so the first test is, does the Z coordinates of P and Q overlap? So let's say I've got 2 polygons, I'm testing them. Okay, I want to know whether 2 of these polygons is going to cause me a problem. Okay, so do the Z coordinates of P and Q overlap? In this case, on the left, they don't. So I haven't got a problem. Okay, I could just move on to the next 2. But in this case, we may have a problem. Okay, because P and Q do overlap, we have to check whether this is going to be a problem. So the next test is, do the X coordinates overlap? Okay, so P and Q overlap, which means we may not be able to tell which is in front and which is behind, but do the X coordinate overlap? If they don't, we haven't got a problem. The reason being is because P and Q don't obscure each other. Okay, but if they do overlap, in this case, we may have a problem. Okay. Next, we check the Y coordinates. It's pretty much exactly the same. Do the Y coordinates overlap? If they don't, again, we don't have a problem. If they do, we may have a problem. So we move on to the next step. Does P lie completely the opposite side of the plane of Q from the viewpoint? So the viewpoint's at the bottom. if this plane of Q is here in this dashed line, if P lies on the opposite side, we don't have a problem. But if it intersects it, we may have a problem. Does Q lie completely in front of the plane of P? If it does, that's fine. We don't have a problem. If it doesn't, we may have a problem. And finally, the hardest thing to check is, do the projections of P and Q overlap? So each of these tests, starting from the beginning, okay, each of these tests are we start with the easiest to test and we go to the hardest. So if something passes the easiest test, that's fine. We haven't wasted any effort doing the harder tests. Okay, and that hardest test is actually having a look at this. If this happens to be the case, but you get to this one and all of them show that we have a problem, what we have to do is we have to cut up polygons. So for example, let's say these two give us a problem. What I can do is I can split this vertical polygon into two, the top part and this bottom part. Okay, cutting polygons like that is unavoidable. We can't get around it. Okay, on Friday, in the second lecture on Friday, we'll be looking at a method that actually tells us which polygons we need to cut or not. Okay. By the way, Newell's algorithm, I'm not going to ask you to ever implement it. It's not something to implement on your assignment. It's just part of the sort of process. But if you are having a look at painters, you have to do it. But it does get a bit tricky, so we won't be doing it on our assignments. Okay, so once you've got the back facing, once you've got painters, that's what you're left with. So look at this. This is a clipped image. It's been clipped, it's been back face code, and it's had painters applied. And what I want to show you is, if I can grab it off Tinterweb. And then a Matlab, I've got this sort of working in action. Okay, so what I'm going to do is just going to run this, and this is a kind of, hopefully if it works. Wrong window. There we go. This is going from sort of like the world space. Oh my word, this is slow. It's a lot quicker on my machine. Okay, guys, so this is going from the world space. This is doing what you did the alignment with the sort of rotating so that the viewer is at the origin. This is the screen space, so this is the perspective projection. This down here has been, down here has been clipped to the unit cube using the clipping, which is kind of your stuff from assignment 7. Okay, this bottom one, I'm going to have to run it again. Okay, this bottom one isn't working very well. Oh, this is weird. It's looking a lot different when it does on my machine. Oh well. This one, yeah, I don't know what. It looks see-through for some reason. Yeah, this computer's rubbish. Anyway, this one was going to be the one with the backspace polygons removed, and that's the one with Painter's algorithm applied. I don't know why it's showing up a bit weird. If I go back to the, that's what it should have shown with backface. Okay, and then when you use Painters, that's what you get. Okay, essentially that's Painters. So that's what I wanted to. Holly, don't. How old are you guys? Come on. Don't start playing with each other's hair. It's just, you know, where is, oh, there it is. Sorry. Right, so that's Painter's algorithm. What I want to do now is talk about the assignment 8. Okay, so I'm going to give you some tips, hints and tips here. So I'm going to bring up assignment 8. Now you all start paying attention now, don't you? soon as I mention assignments, right? By the way, clipping, that's sort of, I'll allow you to work on it this week, even though the deadline was on Friday. In this term, we've got 6 remaining. So as long as you sort of get the 6 in before the deadline date, which is week 24, I'm okay. What I don't want you to do is start sort of backloading them up. So get them done, get them out of the way, and work on the next one. Okay. It has happened in the past when we set these assignments and we don't put any deadlines on them, people start sort of handing in 12 at a time at the end of the year. And I'm like, right, don't do that. And you're working on too much, okay? Right. A couple of things about this hidden surface removal assignment I want to mention. These were written back in the summer, okay, before I saw Killian's notes, and Killian used a different convention than I did. Okay, so these are coordinates, homogeneous coordinates. Notice the ones are all on the far right column. Okay, you should transpose this so ones are on the bottom. So at the moment, this is the columns are X, Y, and Z. It should be transposed so the rows are X, Y, and Z. Okay, and instead of coord, call it verts. Okay, so just to be consistent with all of the other stuff and also the lecture notes. Okay, hidden surface removal. This is a tetrahedron defined by these homogeneous aligned world space coordinates and the polygon linked list. Essentially determine which the sides of the tetrahedron are front facing and which are back facing. So when we did the on the 9 a.m. lecture on Friday, we did a activity which essentially was that question. Okay, and just those of you who were there, you could just go through that one. Yeah, you see, those of you who weren't there, a bit harder. Okay. Question 2, write a Matlab program that loads in polygon linked list and vertex coordinates of Newell's teapot. Okay, and I've put the teapot.map file on Moodle. Okay, so here we are, teapot.map. Okay, I'm going to download that. Okay, and what I'm going to do is I'll just show you what it contains. Where's all my, got too many windows now. There we are. So if I was to load teapot, okay, it gives me the verts, okay, 3,872 vertices, gives me poly, lots of them. How many, okay, 3,200 polygons, and gives you n-verts, just 3,200, lots of fours, because they're all squares. Okay, so what you need to do is essentially load in that data file. Okay, so if I load teapot, that loads in the data. Okay, then what you need to do is loop through all your polygons. Okay, so poly is a 3,200 array by 4. So there are 3,200 polygons in here. So this I equals 1 to size poly 1. Size poly 1 will be 3,200. Okay. You then need to plot the current polygon. Okay. So essentially, I'm telling you how to do, or showing you how to do question 2. The reason I'm showing you is because question 2 is kind of like setting it up for the real question, which is 3. Okay. What we need to do now is for each polygon, you need to loop through the vertices. Because what I want is I want to create an X, a Y, and a Z array for plotting. Okay, so the X coordinate. Okay, so J is each corner. So 4 corners in each of my squares. So the J goes 1, 2, 3, 4 because it's the 4 corners. Okay, well I need the vertex corresponding to whatever polygon I'm on. So I'm on polygon I, and I'm on the jth vertex of I. So vert poly ij. Okay, that will give me whatever vertex, but for the x coordinate, we use the first row. With homogeneous coordinates, we divide by that fourth scaling factor to give us our Cartesian coordinates. So you'll have a 1 by maybe hundreds, 4 by hundreds array of vertices. If you divide the whole first row by the fourth row, the whole second row by the fourth row, third row by the fourth, and fourth by the fourth, you get your Cartesian coordinates for your screen space. So that will mean you'll then have all ones on the bottom. Okay, the clipping, the Sutherland-Hodgman, the code is essentially the, I've got sort of placeholders with what they call question marks. That's essentially putting in the Cyrus-Beck code, and you have to add something to an end of a list. So just to remind you about adding to an end of a list, I'll go back to the, okay, let's create a list. Okay, let's say I wanted to add a number to the end of the list. The easiest way to do it is to open square bracket A followed by the number I wanted to add. Okay. So that concatenating, that's just putting together two arrays into one. Okay. And that's what you need to do for the Sutherland-Hodgman MATLAB. And then do it for the unit cube. Okay, and finally, if you've done all that, you can then try and do it for your virtual world. Once you've got your Sutherland-Hodgman code, it's just a matter of copying and paste it to the other skeleton codes. Okay, because the skeleton codes have the question marks put in as placeholders. Any other questions regarding that? Okay, well, obviously, if you got any additional questions, just come and find me in the tutorials, and I'll do my best to help you. Okay, so I think we've finished a bit early for this morning. As I say, Painter's algorithm, not a lot you can say about it. Just render the furthest polygons and end up with the closest polygon. Hopefully that screencast did work. So if you want to go back over the MATLAB for when I was drawing the teapot, hopefully that's up there. But we'll see.